Hello, everyone. My name is Kelly Hall. I'm a marketing coordinator for ALS North America. I want to thank you all for joining us today for our Webinar Wednesday series. Our presenter today is Joanna Wasik. Joanna graduated as a chemical technologist from Northern Alberta Institute of Technology in 1988. While completing her studies, she worked as a lab technician at Dow Chemical at Fort Saskatchewan. Joanna was responsible for processing QC samples and maintaining lab instrumentation. After graduating, Joanna joined ALS as an analyst in the organic department. For the past 20 years, she has gained extensive experience in environmental laboratory operations as an analyst, team leader, supervisor, and manager. Now Joanna serves as a laboratory manager at our ALS Alberta laboratory. Today, Joanna will be discussing general chromatogram interpretation and BIC scale interpretation. During this presentation, feel free to use your Ask a Question or Raise Your Hand feature to ask any questions throughout her presentation. Joanna, thank you for taking your time to deliver this presentation today. I will go ahead and turn it over to you.
Thank you very much, Kelly. Good morning, everyone. Welcome to our presentation. And well, let's just start talking about chromatograms and how we interpret them and about the BIC scale. And hopefully at the end, everybody will have their questions answered, or if there are more questions, we can follow up on those. So the objectives for today's actually, sorry, before I go, I hope everyone hears me well. Okay. So the objectives for today's presentation is to go very quickly over the hydrocarbon analysis, the definitions on what they mean, looking into instrumentation which is used to provide the gas chromatography and the detectors, introduction to chromatograms, going over the carbon ranges and boiling point ranges, looking into the hydrocarbon distribution reports, we call them chromatograms in overview, evaluating them, looking at the weathering evaluation. We'll discuss BIC scale, and we'll look also in additional factors like site history, chemical data, and any other options which are open for the analysis. So looking at the hydrocarbon analysis, so hydrocarbons are mainly comprised of carbon and hydrogen. There are many different configurations possible. So we can have saturated, unsaturated, cyclic, aromatic. There are basically thousands of compounds found in crude oil and associated petroleum products, which makes it very difficult to report all of them. Instead, empirical aggregate parameters, which we call them carbon fraction, are used to characterize the hydrocarbon contaminations. And so those are the fractions which were determined by Canada standards, the CCME petroleum hydrocarbons, we call them. And they are used the F1, F2, F3, F4, and F4G fractions. So these fractions are designed to distinguish between petroleum product types. We'll be mainly looking at the F2, F3, and F4 fractions at this time. So lab generates results using gas chromatography. It's a method of separating components of a mixture so they can be measured, or we call it detected. So usual gas chromatograph consists of oven, long thin glass column which contains the material that binds to components of the sample, injection system, detector, and a carrier gas. The sample is injected, vaporized, and pushed through the column by the carrier gas. Sample components interact with the column with different affinity based on the boiling points. So that will result in different rates of elution through the column. So obviously the lighter hydrocarbons will come off the column faster, the heavier will stay longer. As each component exits the column, it is measured by the detector, and this is expressed as a peak at a certain time. The time of the peak, the component's elute can be used to ID the component, and the size of the peak determines the concentration. So the bigger peak, the higher concentrations we have. So gas chromatograph, the most popular, they are flame ionization detectors. So we call them FID. So they are used for aggregate parameters as the detector uses the flame to burn hydrocarbon and carbon bonds, it's causing the response. So that way it will create a peak, and the response is proportional to the concentration. This detector is quite universal. It's not non-selective as opposed to the mass spec or ECD detectors. Therefore, it's not really doesn't provide higher detection limits, so it's less sensitive method. The other detector which is commonly used is a mass spectrometer, we call it MS. Is used to identify specific compounds between the mixture. When we look at the mixtures of BTECs or pHs, the sample is broken into charged ions that have a unique fingerprint, which we call it mass spectrum. So on this slide, you can see the typical example of the mass spectrum for toluene, and this can be used to identify the specific compounds. So mass spectrometer is a very selective method, therefore we can provide much more lower detection limits. So as in addition to the F224 results, as ALS supplies the results to the client, we also supply the associated picture of the sample, which we call it hydrocarbon distribution report, or just chromatogram for short. Looking at the chromatogram, those are produced from the GCFID analysis of F224 analysis. So the usual peaks which are showing up on the chromatogram, they range from C10 to C50 carbon. So they exclude F1 fraction, which is run on a different instrument for volatiles. So looking at the chromatogram, we have two axes. There's a y-axis, which is recording the peak height in millivolts. So peak areas are proportional to the concentration. So the higher peak, the bigger concentration. An x-axis, which is recording the retention time, which is measured in minutes. And it basically corresponds to the carbon range, the boiling point. So the chromatogram picture can be used to help characterize the contamination type in your samples. There are a few things to remember, expect minor variation between chromatograms. It depends how long the columns are, how fast the GC ramps, the temperature. So it can provide valuable qualitative information, and if you compare it to the ALS hydrocarbon library, you can recognize the pattern. So in this example, we are looking at the straight alkanes standard from C10 to C40. So it is a typical chromatogram which shows the carbon ranges and distribution. So moving forward, we'll look deeper into the chromatograms to see what we can learn from them. Chromatograms are a good example of where a picture is worth of 1,000 words. There is a lot you can read if we know what to look for it. So obviously there are some limitations to chromatograms. So it is important to understand what not to expect from simple review of chromatograms. So without additional information, we can't provide defensive source and identification. For example, we can usually characterize a contaminant as a gasoline range, we can say, or middle distillate range, or lubricating oil or residue fuel range. But we often can't differentiate much further than that, especially after the weathering process. We can't provide accurate weathering or age dating information when we look at the chromatogram. It's just not accurate, but we can often say whether a contaminant appears fresh or moderately weathered or it's severe weathered, and that's based on the look of the chromatogram. And if you are looking for legal defensibility or expert testimony, you need more than just chromatogram interpretation. There has to be more of the forensic testing. So we actually have come up with 6 easy steps to interpreting what we call the hydrocarbon distribution reports, or HDRs. So first of all, we look at the carbon range. We have evaluate the carbon range, the boiling point range. The second step, we assess presence, absence of the unresolved complex mixture. We call it UCM. We look at the discrete peaks. We try to assess them. We compare the chromatograms with the hydrocarbon library, which is available on the ALS website. We assess potential weathering impact for the petroleum hydrocarbons, and we review any other available chemical data and site history which can help us.
In a moment. We'll start in a moment.
Sorry. Which will help us with the site history. So also there are additional analysis options like GCMS characterization or optional silica gel column cleanup, which can be done to help with determination of further presence of petroleum hydrocarbons. So moving to step 1, it's probably the easiest one, determining the carbon range. So usually we look at the chromatogram and we try to figure out the carbon range of unknown contaminant, which can give important clues to possible sources of or identities. So gasoline range is usually from C4 to C12. Diesel ranges from C9 to C23. Lubricating oils and greases are past C20. So start by looking at the N-alkane indicators at the bottom of your HDR report, or if necessary, maybe look at the actual C10 to C40 alkane chromatogram from the HDR library. It is important to understand that carbon range only refers to the retention time of an alkane marker compounds. So it's actually more related to the boiling point range than it's to the numbers of carbons. So, for example, for branched alkanes, they will elute earlier from the GC analysis than straight chain alkanes. So, and this is a very good example on this chromatogram, Pristane, which is C19 branched alkane, will elute actually well before the C19 straight alkane. So this is to be aware of. In step 2, we are going to look into the unresolved complex mixture, if it's present or not. UCM, we call it, is comprised of thousands of compounds that can't be resolved by the GC separation technique. Therefore, they displayed as a hump on the chromatogram. So we can see here on this slide typical examples of the UCM in petroleum products. So the chromatograms of most petroleum hydrocarbon products will contain a significant UCM, especially crude oils and middle and heavy distillates like diesel, kerosene, fuel oils, lubricating oils. So it's good to remember that actually there are few products, and let's say gasoline, it's not going to show the harm because many contain the very light hydrocarbon compounds. Naphtha is the same, they won't show up the UCM unresolved complex. Moving to the next step, looking at the discrete peaks assessment. Looking at the chromatogram, we will be seeing discrete peaks, and they can tell us certain things about our source. So evenly distributed peaks of N-alkanes, mix of odd and even N-alkanes usually indicate petroleum products. If we have only odd N-alkane, straight alkanes, that usually pointing to natural organics like peat moss. So in those cases, we can use GCMS characterization to try to identify large discrete peaks, like let's say if the pHs are present, if they dominate the chromatogram, this may be an indication of creosote. Creosotes usually contain up to 70 to 80% of non-alkylated pHs. So to actually confirm presence of pHs, we recommend GCMS analysis. So this is something to remember. We cannot really say if the pHs are present just looking at the flame ionization chromatogram at the FID analysis. Alkylated pHs are commonly found in fuel oils, but they are not easily visible into the chromatogram. So sometimes they are not that visible. Sharp peaks, usually those are the non-polar or medium polarity compounds. Broad peaks usually would be more polar compounds, which can sometimes be also indicative of natural organics. So looking at this chromatogram, that's a typical diesel standard chromatogram. So we can see the straight alkanes are displayed, very nice sharp peaks in a series of sharp peaks which are evenly spaced. So because they are very evenly distributed, so they are quite easy to find on your chromatograms. And as the chain of the N-alkanes becomes longer, obviously the peak shapes become smaller and wider. So the presence of the alkane peaks and the UCM complex is a strong evidence for the petroleum hydrocarbon contamination. So this is the example of the diesel chromatogram, and we have another example of the natural organics example, that's for musket, for peat moss. So they are usually indicated by many discrete peaks, like we can see it on this chromatogram, particularly past C19, and they are the odd hydrocarbon peaks. Majority of those peaks will lie between C19 and C32 range, and they are quite visible, and obviously there is no presence of the unresolved complex mixture. So most of the natural sources won't, if they are clean, they won't have the UCM. So plant waxes will contain all the alkanes from C21 to C33, so that's a very good example. So moving to the step 4, where when we compare our chromatogram to the library, so like I mentioned before, ALS has a library of common petroleum hydrocarbon chromatograms, which are available on the website. So we will compare our sample chromatogram to the ones which are available in the library. One thing to remember, the library consists of pictures of pure sources of petroleum products. So sometimes the hydrocarbon of your sample may not look exactly like the one which is in our library, especially if the sample was exposed to a variety of processes in the environment and it's weathered, so it won't look exactly the same. But this example, gasoline is the one which doesn't have the unresolved complex mixture, and in Creosote's pHs also they are quite separated peaks. So moving to the step 5, which is assessing the petroleum hydrocarbons weathering. So we'll look at any potential effects that the environment has placed on your sample through weathering. So there are 3 important mechanisms which will change the resultant chromatogram. So those will be evaporation, so evaporative weathering, so loss of, usually it's a loss of volatile fractions, biodegradation, so when your sample is exposed to a microbial biodegradation, so it will happen selectively by bacteria impact. And water washing, it's a selective fractionation by groundwater. So moving to the first weathering process, which we call it evaporative weathering. As your sample is exposed to the air, the evaporation process selectively removes the volatile compounds. The rate of the process is obviously dependent on the environmental conditions, so it will obviously affect a lot of samples from the spill in the environment and exposure when they are exposed directly to the air. When the soils, let's say if we sample deeper in the ground, so depends of the depth. So the evaporation process will be slower. So we may talk here about the differences days versus actually months and years, depends how much to the air sample was exposed. And the evaporative losses are rapid at the surface. You know, the components with the boiling points up to C16 will evaporate quite fast. So those are usually up to 300 degrees Celsius boiling points. When under the surface, the subsurface, evaporative losses are much slower. So usually, typically they are seen for the hydrocarbons up to 215 degrees Celsius boiling point, so we are looking around C12. Also, this may depend to the soil texture. So obviously the compacted soil, in the compacted soil, the rate of evaporation will be slower than in, let's say, gravel or sand due to the nature of it. And we are looking here, actually, we have an example of the evaporative process on the diesel standard. So we try to mimic this process in the lab. We evaporated pure diesel by 25%. And when you compare those two chromatograms, you can see that losses of components are targeted in the C9 to C12 range. So those are the lighter components. We were in the 25% evaporated diesel. You cannot see those peaks. They disappear, they are gone. Looking into biodegradation, so biodegradation happens from microbial activity, and it's another very important process that will affect the petroleum products exposed to the environment. So the table in this slide shows typical order of removal of components from the least to the most stable. And the stability of the components is related to the complexity of the molecules. So the chain length, the branching, the rings. So as the complexity of the molecule increases, the rate of biodegradation decreases. So it's harder for the microbes to break down the longer chains of hydrocarbons or branched ones. So this information can be used to determine how weathered or how old sample is actually. So for the middle distillates like diesel, the N-alkanes will biodegrade very rapidly. And for the highly branched alkanes like isoprenoids, they will be more resistant to the weathering. And this is a typical example of chromatogram of the diesel to again pure source, when you can see the N-alkanes dominate, and you can see the very good actual separation of the peaks of pristine and phytane. Those are the branched alkanes, so a lot of light and peaks. And as you move farther, the branch peaks get a little smaller. So typically in the pure source, the fresh soil, the ratio of the C17 to pristine will be around 2 to 1. And when you move to look at the severely biodegraded diesel, like this chromatogram here, so the alkanes are completely removed. So first the small chain and after the larger chain. So you can see that most of the light and hydrocarbons are completely gone. The isoprenoids, due to their complexity, are not as much affected. Therefore, they are more prevalent now in the chromatogram. You can see the pristine and phytane peaks. So the ratio will decrease. Eventually, they will disappear too. It depends how long the sample is exposed to the elements. And the last one is the water washing. So petroleum products contain some water, sorry, excuse me. So they do contain some water-soluble components, and when exposed to water, they will be preferentially removed, or we call them washed away. So the rate of removal is determined by the relative water solubility of the compound. So the chart in this slide shows the water solubilities of some compounds that are commonly found in petroleum products like gasoline and diesel. And so obviously ethanol MTB will wash out first, after benzene, toluene, ethyl benzene, and xylenes. The heavier alkanes and aliphatics, which are practically insoluble in water, and they will stay. So this basically in the system where there is an underground release exposed to groundwater, this process will affect both the groundwater and the soil contamination. So the water concentration will increase during the washing, and the soil concentration will decrease. So looking at the chromatograms of the example of the water washing on the diesel, so we try to recreate this process in the lab with diesel to mimic a single washing event. So pure diesel was shaken with water one time, and the water was then analyzed to see what components wash out. So in the pure diesel product, you can see large unresolved complex mixture and a lot of discrete peaks, alkanes, isoprenoids, which will dominate. In the water-soluble fraction, the UCM is basically gone. Why? Because it's largely water insoluble, so it didn't wash out into water. When looking at the petroleum hydrocarbon chromatograms for water samples, it is worth to remember that they might look very different than actual pure sources. Many components of petroleum products will preferentially be found as film, so they won't dissolve, or they will stay in sediment. Therefore, their presence in water sample will cause the chromatogram look a little more differently than the library. And we should also consider other data when we are evaluating our chromatograms. So we need to review the site history and phase investigation. That data will help us in determining what to expect and what analysis to conduct. So if, let's say, if we suspect gasoline, so obviously we should be testing for BTEX and F1. Gasoline contains around from 10 to 20% by weight of BTEX. If diesel or fuel oils are expected, so we should be looking into the review of F224 results and conduct maybe analysis for alkylated pHs analysis. And it is because they are present. Up to 20% of alkylated pHs will be found in the fuel oils. And also, if we are thinking that there may be results or coal tar suspected, so look at unsubstituted pHs, so straight pHs. They contain around 70 to 80%. There will be increases or coal tar. Obviously, we'll be looking to use GCMS characterizations when appropriate to make those determinations. So moving forward to biogenic interference calculation scale, which we call BIC. So the Canada-wide standards for petroleum hydrocarbon analysis in soils provides the protocols and primary technical basis for the Alberta Tier 1 petroleum hydrocarbon soil remediation guidelines. The CCME analytical methods quantify the petroleum hydrocarbons as F1, F2, F3, and F4 concentration for light to heavy hydrocarbon products such as gasoline, diesel, crude oil, bitumen, asphalt, motor oil. So extractable organic compounds are assumed to be petroleum hydrocarbons unless proven otherwise. And F224 analysis is not specific to petroleum hydrocarbons. So we can also find in those fractions biogenic compounds. We call them biogenic carbons, and they can be falsely detected as petrogenic hydrocarbons in uncontaminated organic soils and compost materials. And that's when we see the false positives, which may come from muskeg, vegetations, manure, wood waste, and similar tissues, sewage. So looking at the current slide, actually 2 slides, this one and the next one, we are going to look at comparison of the petrogenic versus biogenic petroleum hydrocarbons in crude oil and after in the diesel. So the carbon distribution pattern was observed, and this was the study which was actually conducted by Francine Kelly-Hooper and the University of Waterloo, between others. And so there was a study conducted on 100 clean and petroleum hydrocarbon contaminated samples. And it was determined that sometimes there is an exceedance for the results in F3 fraction, which is not caused actually by the petrogenic compounds, but is caused by the biogenic compounds. So the subfraction F3 was determined to be dominated in clean oils and manure compost samples, and where subfractions F3A and B were approximately equal in the concentrations in the crude oils. And this slide actually displays that difference. So when we look at the diesel samples, it's a very similar conclusion was drawn, and that subfraction F3 dominated in diesel waste. F4 was only detectable in petroleum hydrocarbon sources, but the biogenic organic carbons were causing slightly contaminated soils to exceed the Tier 1 guidelines for F3 hydrocarbons. And that's the F3 fraction, which is showing in the diesel with manure mixture and manure. And in conclusion to this study, and the biogenic, the BIC scale was developed to actually approach the resolving on the false positive petroleum hydrocarbon exceedances. So BIC scale is a mathematical approach, and we are only looking at the crude oil and diesel contaminated soil sites when we talk about BIC scale. And it helps to eliminate false positive exceedances in the F3 fraction. But there are some conditions for the proper use of that formula. So one of those, so the conditions are that F2 concentration have to be less than 30 milligrams per kilogram. So basically those are the Tier 1 soil guidelines. So they cannot exceed the Tier 1 soil guidelines. The F3 concentration have to be detectable, but may exceed the Tier 1 soil guidelines. F4 concentration are detectable, but do not exceed the Tier 1 soil guidelines, and greater than 85% of the total F3 range occurs between the F3B range. So looking at the distributions, the summary of the study which was conducted for the distributions of F2, F3, F4, and the F3AB subfractions in diesel, crude oil, engine oil, asphalt, and peat. So we can see the differences. So when there are petroleum hydrocarbon contaminations present, like in diesel fuel and crude oil, there is a very high F2 fraction and very low F3 fraction. When we look at the engine oil, we see trace of F2, very high F3B fraction, and the same is F4G may be detectable, but it's going down. The same is with asphalt, traces of F2 and high F3. And the same is actually observed in the peat samples, traces of F2 and high in F3B. So this picture, which is very, I think, very common, like a lot of people saw this picture, it summarizes where actually the BIC scale can be used and when it cannot be used. So obviously we cannot use it for engine oil and asphalts because they mimic almost the same ratios what we see in the clean peat samples when the exceedances for F3 fractions are above the Alberta Tier 1. So Alberta Environment and Parks Land Policy provided detailed instructions how to apply F2 and F3B subfractions concentrations to the BIC scale in order to determine if organic samples have falsely exceeded Alberta Tier 1 guidelines for the F3 fraction. So first of all, obviously there has to be quantitative test results provided for F2 to 4 analysis. Second of all, the chromatogram evaluation has to be done. So chromatograms, comparing the chromatographic profiles from the CCME F2 to 4 test method. So if they are consistent with typical profiles for muskeg or organic soils, we need to look for visual evidence for the presence of typical petroleum hydrocarbon product profiles, which are evident in the F224 chromatograms, and obviously evaluating of F2 concentration. So F2 has to be less than 30 milligrams per kilogram. So if they are detected above 30 milligrams per kilogram, which is the maximum limit is for F2, so obviously this will be limited to be applicable to the BIC scale. Now, when doing the calculation, if the F2 concentration are less than detection limit, so if the lab is reporting 30 ppm as a detection limit, so for the calculation purpose, we should use the half of the limits of reporting. So in this case, we'll use 15. So total organic carbon results have to be evaluated, so they have to be consistent with organic soil. So usually the TOC values have to be either equal or more than 17%, so those are the typical numbers for the organic soils. Peat samples have more than 40% of the TOC, and in compost samples we can see from 50 to 60% of TOC. And the last one is the BIC value. So actual the BIC evaluation and the calculation of the BIC index has to be less than 10%. So in this case, it will indicate potential for false exceedances of the petroleum hydrocarbons in F3 guidelines. And lastly, the opinion or evaluation of the BIC model to listed sample has to be provided. And that usually comes in the form of a professional letter. So ALS is providing analytical packages to calculate the BIC scale. So currently we provide 2 packages, 2 analytical packages. One is including the BTEX F1 to 4 analysis with the F3AB split, calculating BIC ratio and TOC analysis. And the other package provides only the results, the analysis and results for the extractable hydrocarbons. So if let's say if you don't suspect that there are volatiles in it and you don't feel there is a need to test for F1 and BTEX, so that one will test for F2, F3A, and F4G and BIC ratio calculation with the TOC. And we also will provide the formal professional opinion letter if required. So there are a few things here for the professional opinion letters. They can be done later on. So let's say the analysis can be requested. And this is what we tell to all our clients. We're asking them to request the analysis beforehand. So why is like this? Because basically BIC ratio is just a calculation, and the F3 A and B is a split when we understand that we can recalculate later. And it is true. In many cases, this can be done later on after the F2 to 3, 4 analysis, but we would recommend to ask it upfront, just in case if there's any other supporting analytical work required. So let's say maybe we need to run GCMS analysis for the pHs. Also, hold times for the samples have to be considered. For all the soils, it's 14 days from the sampling. If the other petroleum hydrocarbon contaminants are present, in addition to the background from natural biogenic hydrocarbons, if this analysis is not requested upfront, later on, maybe past hold time, maybe results won't be valid. And the formal professional opinion letter can be requested later. And here actually we have an example of ALS formal professional opinion letter. And this letter will contain all the qualitative results requested and will also provide the chromatogram evaluation and the opinion stating if the chromatogram looks like petroleum hydrocarbon or not. So there are also other additional, I would say, other options for the analysis. So if they are unknown GC peaks, we can use the GCMS characterization, which will search against mass spectral library of like almost 700,000 compounds. And so the common chemicals can be often easily identified. And this is something to remember, that ID is not conclusive unless it's confirmed with reference standard, and that's what is important to remember when we do GCMS characterization. It is very useful to provide evidence for natural organics versus the petroleum hydrocarbons. It is not much useful when there is a UCM present. And also the GCMS characterization is not very useful if we're looking at analyzing the obvious petroleum hydrocarbon products, which are very obvious. The other option here to do is to conduct silica gel column cleanup on the sample. Silica gel column cleanup treatment will remove the polar organic compounds from the sample, so fatty acids, humic acids, also if there's a biodegradation of petroleum components, those will be removed too. So it will have little to no impact on most unweathered petroleum products like alkanes, aromatic hydrocarbons. Petroleum hydrocarbon UCM will not be removed, so it will be still present. So this can actually, the silica gel column cleanup can offer clues to the nature of your sample. So if basically the tool, how it works is the sample gets, the treated and untreated samples, they get analyzed and the results get compared. And based on that comparison, it can be determined if majority of the components in your sample are polar or non-polar. So basically that's how it works. And that will conclude our presentation.
Wonderful. Thank you, Joanna. We will go ahead and open up for questions. You may write your question in your Ask a Question box, or you can use your Raise Your Hand feature if you would like to ask Joanna a question directly. We'll give everyone a few moments to write those questions down or to raise your hand. While we are waiting, I just wanted to let everyone know that we do record these webinars. We do post them on our YouTube channel. It's under ALS Limited. And then you can click on the North America playlist. We upload all of our Webinar Wednesday series presentations as well as a wide range of other video resources.
I'm not sure. I don't hear any questions. Is everything working well or? Hello?
I have a question from Bob. He says, could you expand a bit on silica gel cleanup, especially the elimination of weathered PHCs?
Right. So if we look at the BIC scale, I'm not sure if that question has to do with the BIC scale or not. But if it has to do with the BIC scale, so we don't like it's not recommended to use the silica gel column cleanup. So it's only the in situ use. Because it will remove like if we deal with the polar compounds, it will actually remove most of them. So the BIC scale won't work for it. So it's actually not allowed to treat or double treat the samples by silica gel cleanup, by the column cleanup, or double treatment by silica gel in situ cleanup for the BIC scale. Regarding the silica gel cleanup, we're talking about column cleanup, yes? I think. So
yeah, it said especially the elimination of weathered PHCs on silica gel cleanup.
Okay, so the weathered petroleum hydrocarbons, if they are broken down, and they will be partially removed by the silica gel cleanup. So that's why what we were saying, that usually the silica gel column cleanup is very effective for samples which contain polar compounds and the unweathered petroleum hydrocarbons. Now with the weathered ones, depends how the weathering process went. So if there's a microbial degradation, they will be broken down. And it's possible that some of those byproducts from the microbial degradation, they will become polar and they will be removed by the silica cleanup. So if like from this lab standpoint of view, when we perform the testing, if the client knows that the sample is heavily weathered, we would probably recommend to do straight analysis first and after do silica cleanup to see actually how much of the hydrocarbons, the weathered hydrocarbons, were affected by the treatment. Because silica will pick any polar component. So that's what will happen.
Wonderful, thank you.
Sure. Yeah.
He does say thank you, so I think you did answer that question. And Bob, we do have Joanna's email address that will be posted later if you would like to contact her for any follow-up questions. We have another question from Amy. She says, is there a way to differentiate natural F4 exceedances?
Not really, because F4 is usually coming as an unresolved complex mixture most of the times, because those are the heavier hydrocarbons. And it's really hard to say if there are any biogenic compounds. And it's the same when the study was performed on the pitmos samples. Most of those contaminations were in the F3 fraction, and when we could see the resolved peaks. But sometimes F4G may have actually some of the organic compounds, like the polar ones, with the unresolved complex mixture from petroleum hydrocarbons. So you may see the hump and actually some peaks on it, and it's very hard to resolve those. We look into that in the lab, and so the only way is to, when the silica gel cleanup is done, the in situ silica gel cleanup will remove some of the polar compounds and clean up. But if your sample has it is of a nature of actual like organic source, not the petroleum hydrocarbon source, we won't be able to differentiate on F4. Unfortunately, that's the truth.
All right. Well, thank you. I don't see any additional questions coming in. I think on your next slide you have your contact information. Is that correct, Joanna?
Oh yes, I'm sorry. I always forget about
And no
this.
worries. In case I know that some people had a little bit of complicated questions. I'm probably going to follow up with a few of them, but in case anyone else wants to reach out to Joanna, here's her contact information, as well as the lab information. Well, thank you again, Joanna, and again, thank you to everyone on this call today. Enjoy the rest of your week. Have a great day.
Thank you very much, and goodbye.